Every day, millions of people in the US drive their cars to get wherever they need to go, often without a second thought. Whether it's driving to work, going to have fun, or taking a road trip, people are dependent on cars to get them wherever they need to go. However, with so many people driving together, it is inevitable that there will be crashes that occur. Fortunately, there are many safety features developed and implemented to keep the drivers and passengers of these cars safe. These safety features are very diverse and vary from the overall structure of the vehicle during the collision to seatbelts and airbags that engage during the crash itself. However, all the safety features work together to address the basic laws of physics that lead to injury for vehicle passengers. So, what do all these features have in common? It all boils down to the principles of inertia and momentum. Inertia is the property of matter that resists change to motion. Back in the 1600s, Newton explained how this property operates in his first law of motion, that states an object in motion will stay in motion unless acted on by an outside force. Momentum, on the other hand, is essentially the quantity of motion and is equal to the mass times the velocity. This is typically given in the unit Newton seconds and is described by the equation P equals mv, in which P stands for momentum. M is the object's mass and V stands for the object's velocity. Thus, a small object with a higher velocity could have the same momentum as a larger object with lower velocity. For example, a truck with a mass of 2,000 kilograms and a velocity of 10 meters per second, and a car with 1,000 kilograms going 20 meters per second would both have the same momentum of 20,000 Newton seconds. Newton's second law of motion, the law of mass and acceleration, describes how the net force on an object affects the acceleration of an object with certain mass. Typically, this formula is represented by the equation F equals ma, where force is equal to mass times acceleration. Now, however, if we understand the acceleration is just a change in velocity over time, we can rewrite the same equation as F times m delta v over t, which is force is equal to mass times the change in velocity over time. In fact, when talking about force and inertia, Newton spoke in terms of changing momentum with an impulse, which is given by the final equation F times t is equal to m times delta v. The right side of the equation is called the impulse. The impulse is the force applied over the time taken to change the momentum. As you can see, the left side of the equation is the change in momentum, as it is the mass of the object times the change in velocity. This means that the force is required to change the momentum of an object will be higher if it occurs over a short period of time. Conversely, if the change in momentum occurs over a long period of time, then the force on the object will be lower. But as great as all these numbers and equations are, it's nice to have a practical example. Take these two identical eggs, for example. If I drop this egg on a hard surface, such as this plate, the momentum of the eggs will drop from its velocity to a zero in a very short amount of time. This means that the force will be greater over that short time and the egg will crack, like this. However, if I drop this egg from the same height into a cloth, the egg will not crack. As you can see here, the egg is perfectly fine. This is because the cloth increases the distance that the egg travels to reduce its momentum down to zero, which increases the duration of time it takes to change the momentum. This results in a much lower force on the egg, which allows the egg to remain intact. How does this apply to the safety features that we use in our cars every day? Well, say that you're traveling in a car going 30 miles per hour. If you hit a wall without a seatbelt, the car comes to a complete stop. However, your inertia will keep you moving until acted on by an outside force, which will most likely be the steering wheel. When that happens, your velocity goes from 30 miles per hour to 0 miles per hour within a very short period of time. This is a high change in momentum over a short period of time, which results in high forces on your body that can lead to injury or death. In order to combat this, the seatbelt goes across your chest. When you get into a crash, the seatbelt applies the force to your body to stop the momentum and prevents you from continuing to stay in motion. It also increases the time it takes for you to reduce your velocity. Even if this is just a small increase in time, it can result in a much smaller force on your body, which could lead to less severe injury. In the same way, the airbags in your car deploy when you get into an accident. The airbag deploys so that you hit it before you hit any other solid objects in the car. The airbag acts as a pillow and has a lot more flexibility to it, which helps to increase the time it takes to slow your body down to zero, which again reduces the forces acting on your body. Additionally, modern cars are made so that the front car crumples. When getting into a head-on collision, as the front of the car crumples, it increases the duration of the crash. This increases the time that it takes for the vehicle and the passenger seat belted inside to reduce their velocity to zero, and even further reduces the forces on the passenger inside. These increases in time have drastic impacts on what the driver feels inside the vehicle during a crash. According to the CDC, wearing a seatbelt alone decreases the risk of death by 50%. Adding airbags with seatbelts decreases the risk of death by 61%. Using the principles of momentum and inertia, physicists and engineers have been able to make incredible strides in making cars safer, which leads to less serious injuries and less deaths on the road for everybody.